In this video, we will look at what's known as parametric equations. Let's consider a curve like this. I have a starting point here, I have an ending point here. This curve cannot be described as y equals some function of x. However, we still need to be able to describe it, right? Because this could represent motion of a particle. Right, t naught. This could be some final time t, right? We could have some t1, right? So the particle will be located there at t1. Could be located here at t2. Right, in this case, we say the motion, right, is going along this way. Well, if we take a look at this point here, right, it's an ordered pair, right? It's the x position at time t and the y position at time t. Well, this is the idea behind parametric equations. So if x and y are continuous functions of t on an interval I, then the equations x equals x of t, y equals y of t are called parametric equations. And t is called the parameter. The set of points x, y obtained as t varies over our interval is called the graph of the parametric equations. This graph is called a parametric curve. And it is typically denoted by C. So what we can do is represent a parametric curve in the form C of t equals x of t comma y of t. And this is called the parametrization of the curve. The direction of increasing t is known as the orientation of the curve. Right. So going back up to the graph considered earlier, those blue arrows represent this curve's orientation. Let's consider a curve, y equals 2x squared minus 3, right? Finding a parametrization of this curve is fairly simple. Since it's already in the form of y equals f of x, just say x equals t, be the parameter. Then notice what we get. We get that c of t would be t, then 2t squared minus 3. And this will be true for all values of t. Let's take a look at a very common type of curve. A circle. And let's say the circle has radius big R, and it's centered at the origin. Well, recall that at any point, the x-coordinate would be given by the radius times cosine of the angle, right, that the radius makes. And the y-coordinate is r times the radius times sine of theta. Well, now what would happen if we do this? That wasn't very well drawn, but that's okay. I can just move it. All right, what happens if we take a circle of radius r, but centered at the point AB? Well, now take any point. How do we describe it? All right. Well, x, we're still going to have r cosine theta, right? But we moved it a units. So it wouldn't just be then a plus r cosine of theta. And we can use a similar argument for the y-coordinate. So this simple observation is going to lead us to a claim. What we claim is we can parametrize, I don't want to word it that way. A parametrization for a circle of radius r and centered at AB is C of theta equals A plus R cosine of theta, B plus R sine of theta. For 0 less than equal to theta less than 2 pi. Let's just say less than or equal to 2 pi. All right, well, let's prove it. So recall that for a circle, of radius r and centered at AB, we would have the quantity of x minus a squared plus the quantity of y minus b squared is equal to r squared. If we plug in the c of theta we just found, notice what we get. We'll get a plus r cosine of theta minus a all squared plus b plus r sine of theta minus b squared. So what we get are these a's are going to drop out, right? These b's are going to drop out. We get r cosine theta squared plus r sine of theta squared, right? That's going to be r squared cosine squared of theta plus r squared sine squared of theta. Factor out an r squared. Left with cosine squared plus sine squared. But cosine squared plus sine squared is 1. So we get that this equals r squared, which is what we wanted it to equal. Right, a full revolution is 2 pi, right? So that shows that theta will go from 0 to 2 pi. So our claim is correct. And it's just going to be formally stated here. This is an extremely important parameterization. Right, it's one that I do recommend. That you write down somewhere and keep it safe. If we are given a parametric curve, C, we are clearly now going to be interested in, at that point, what's the tangent line? Or in other words, what is the slope of C at some point P? Which of course means we want to find dy dx evaluated at the point P. So consider the curve C of t given by x of t comma y of t. Well, then notice that dy dx, I'm sorry, not dy dx, y prime of t, which is dy dt, right? This would be dy dx times dx dt, which is just dy dx times x prime of t well, that would mean that dy dx is equal to dy dt over dy dx. I'm sorry, dx dt, or simplified, y prime of t divided by x prime of t. So formally stated, Consider the parametric curve where x and y are differentiable functions of t. Furthermore, assume that x prime of t is continuous and non-zero. Then dy dx is equal to dy dt over dx dt. Oops. So we're going to consider the curve t squared minus 3, 2t minus 1. And we're going to find its slope, or I'm sorry, we're going to find tangent line for the point where t equals 2. Well, dy dx, right? So first we need the slope. Would be the derivative with respect to t of 2t minus 1 divided by the derivative with respect to t of t squared minus 3. So we get what? 2 over 2t, which is just 1 over t. Right, so equation with tangent line, remember, y equals y naught plus the slope at the point times x minus x naught. So what we can do is convert this and write this as y of t naught plus dy dx evaluated at t naught times x minus x of t naught, right? Where t naught is our point. So for us, we're going to get y equals y of 2 plus dy dx evaluated for t equals 2 times x minus x of 2. Two times 2 minus 1 plus 1 over 1 times x minus 1 squared minus 3. 3 plus the quantity of x plus 2. Right, and so our tangent line. I'm sorry, I'm doing, for some reason I switched from t equals 2 to t equals 1. All right, so let's try again. 3 plus 1 half. 4 minus 3 is 1. So what we get is y is equal to 1 half x plus 5 halves. If we're given a curve with parametrization x of t, y of t. How do we find the second derivative of y with respect to x? Well, we know this. What we can say is this is d dt of dy dx, then times dt dx. But this will be d dt of dy dx times 1 over dx dt. Well, we already know what dy dx is. I'm going to now shorthand this, right? So we get d dt, y prime of t over x prime of t, then all times 1 over x prime of t. Well, we're going to have to evaluate that using quotient rule, right? So x prime times y double prime minus y prime times x double prime all over x prime squared times that by 1 over x prime, and we get that d squared y dx squared is equal to x prime of t times y double prime of t minus y prime of t times x double prime of t all over x prime of t cubed. Let's say we're given some parametric curve, and we want to find this area. Okay. So consider the curve c of t, which is x of t, y of t. Right, for points where t ranges from a to b. Furthermore, x of t is a differentiable function. What we're going to do is start with a regular partition of this interval. Right? In other words, we're going to get a equals t0 less than t1 less than t2, so on and so forth until we get up to less than t sub n, which is equal to b. So the height of the ith rectangle is y of x evaluated at ti star. Right? Where this ti star is some point in the ith interval. The width of the ith rectangle is just delta x, which is x of t sub I minus x of t sub I minus 1. Therefore, the area of the ith rectangle, right, is y of x of t sub I star times delta x. So total area located under C of t would then be summation I, or would be approximated, let's say, is approximately sum I equals 1 to n y of x of t sub I star times delta x. Which equals summation I equals 1 to n of y of x of t sub I star times delta x over delta t times delta t. If we now let n go to infinity, delta x over delta t will converge to dx dt. And delta t will, of course, approach 0. So what we get is that a is the integral from a to b, y of t times x prime of t dt. So let's look at the curve t squared for t minus t cubed. We want to determine the area enclosed within the loop. So what we're going to do is come over to Wolfram Alpha. And let's just take a look at what this looks like. So we're going to use parametric plot. And let's do t from -3 to +3. Okay. So then the region that we're interested in is this area right here. Okay. But notice that this region is symmetrical about the x-axis. So what we can do instead is find this area and multiply it by 2. All we have to do is determine the values for t. Well, notice that we're going to have y equal to 0 at both ends of the loop, right? So what we do is we take the y component, set it equal to 0, and solve for t. I don't know why I did square roots. So t is going to be -2, 0, and +2. Let's just take 0 to 2. Right? We don't need to worry about -2 to 0, right? Because that would be the other half of the area. Now we said it was y times x prime so we get 4t squared minus t to the 4th power. Let's move down, right? So 4 times 4t cubed divided by 3 minus t to the 5th divided by 5. So 2 cubed is 8 times 4, 32. So 32 cubed minus 32 fifths. And then times that by 4. (256/15). Let's say we now, given some parametric curve, we want to find arc length. Right, from some point t equals a to a point t equals b. Well, what we're going to do is construct a polygonal approximation L consisting of the n segments obtained by joining the points P naught, which is C of T naught, P1, which is C of T1, right, up through Pn, which is C of Tn, corresponding to our partition. Which is A equals T naught less than T1, less than so on and so forth, up until we get to Tn, which is B. So if L sub I is the segment joining Pi minus 1 to Pi, then what we get is the length of L sub I is the square root x of Ti minus x of Ti minus 1 squared plus y of Ti minus y of Ti minus 1 squared. Assume that x and y are differentiable. Then by mean value theorem, there exists two values, Ti star and Ti double star, both located in the interval Ti minus 1 to Ti, such that x of Ti minus x of Ti minus 1 is equal to x prime of ti star times delta t sub I, and y of ti minus y of ti minus 1 is equal to y prime of ti double star times delta ti, right? Where that delta ti minus ti minus 1. So what we now have is the length of the ith segment is the square root x prime ti star squared plus y prime ti double star squared all times delta ti, which means the total length of this approximation, right, is the sum of all those L sub i's right, and this gives us an approximation for arc length. Now this is nearly a Riemann sum. Okay? If the ti star and the ti double star were equal, then we would have a Riemann sum. However, it can be shown that this sum is going to approach an integral. All right, and so we're just going to take that fact for granted. Right, and pass this summation through the limit to get the integral from a to b, square root of x prime of t squared plus y prime of t squared dt. All right, so this will now be formally stated. we're going to use this to find the circumference of a circle. So without loss of generality, we may take the center of the circle to be the origin. And say this as radius r. Now recall that this has the parameterization c of theta equals r cosine of theta, r sine of theta, for 0 less than equal to theta less than equal to 2 pi. So arc length, integral from 0 to 2 pi, square root r squared cosine squared theta plus r squared sine squared theta d theta. This is the integral from 0 to 2 pi, square root of r squared times cosine squared theta plus sine squared, which is the integral from 0 to 2 pi of just the square root of r squared. Right, so that's the integral from 0 to 2 pi, absolute value of r, d theta. Right, but the absolute value of r, right, well, r is always positive. So we can just say this is r times the integral from 0 to 2 pi of d theta. Right, so that integral is just going to be the upper limit minus the lower limit. And so we get 2 pi r as the circumference, which is exactly what we got from geometry. So I need to correct the record here. Right, this is not correct. What this should have been was negative r sine of theta squared plus r cosine of theta squared. Right, but then from there, the rest of the work follows. Right, so all we had to do was correct these terms, right, to be x prime, right, and then y prime. If we come back up, and let's say we take this red segment, right, and rotate it about the x-axis. Well, then we get a surface of revolution, right, and we can find its area. The derivation for this is very similar, right, so it's going to be offered without a derivation. So what we're going to do is look at surface area of a sphere. Right? So we can form a sphere by taking a semicircle of radius r and rotating it about the x-axis. So this semicircle can be parameterized by r cosine of theta, r sine of theta, except now we're going to go from 0 to pi, right? We only want half the circle. So what we get is surface area is 2 pi, integral from 0 to pi, r sine of theta times the square root r cosine theta squared. Negative r sine of theta squared plus r cosine of theta squared d theta. This is going to give us r squared sine of theta d theta. So 2 pi r squared integral from 0 to pi sine theta d theta. Right, once we evaluate it, we get 4 pi r squared, which is the surface area of a sphere.